is Syed Ahmed once again, and I'm a computer vision developer working at Ahold USA at the innovation labs there. And I'm also a third-year undergraduate student at Rochester Institute of Technology. So today I am going to talk about transfer learning on TensorFlow in 30 minutes. And 30 minutes, it's a pun. What it is that I hope my talk's not gonna go over 30 minutes. You can train your model in 30 minutes. That's what I mean by this title. So let me get started. So what do I mean by transfer learning? What do we mean by transfer learning? The way, one traditional example is, so for instance, a baby, when it learns to walk, first the parents, they teach the baby, okay, this is how you walk, and suddenly one day the baby starts walking. So now, after the baby learns how to walk, the baby has the knowledge of that, okay, I have to take little by little steps. So next time, the parent just have to say that, okay, now you have to run, but they don't have to teach the baby, okay, this is how you run. The baby can figure it out that, okay, I know how to walk, and just with a little exertion, I can probably run. So there is a transfer of knowledge there. So the baby knew how to walk, and now using that knowledge, the baby learned to run. Another example that was just bugging in my mind was, like, for instance, in college, we have, for the advanced courses, we have something called a prereq. So the prerequisites, for instance, let's say Calculus 2, before you move on to Calculus 2, you have to complete Calculus 1. And once you master all the topics from Calculus 1, you go to Calculus 2 and use those Calculus 1 knowledge into Calculus 2. So that's kind of like what we see in the real life, something of transfer learning. So before I move further, I want to clear where the scope of this talk would be. I will be speaking from a very developer perspective. For instance, right now you hear that, okay, Google's inception model has reached 96% accuracy, ResNet has reached 3.5% error in their rate. I want to tell you what do you get from those trained models. They have trained on 1,000 classes, 1,000 different objects, and now the computer knows, okay, how to recognize a car or how to recognize a train or all those other classes. I want to tell you, okay, where do you go with it? How can I use it in an application, let's say, in a mobile app, let's say. So this is where my talk scope is, and I want to give you a very hands-on approach, something that you can take home right now and start developing apps for it. So the three, what is the recipe for the thing that I'm talking about that you can use this transfer learning on? First one is you need a model. So for instance, you have Google's inception model, you have Microsoft's ResNet. So you need a pre-trained model. You can also retrain your whole model and build on top of that, but that is a very expensive procedure to train a model from the scratch. It would take you 2 to 3 weeks over multiple GPUs and stuff. So you need a model. And the second thing, which is a very interesting component that I encountered in the past month, you need a good data set. So for instance, let's say, let's go back to the baby example where you're teaching the baby to walk. Before you teach the baby to walk, you need to know how to walk. So for instance, one of my uncles used to complain that I walk with my feet, with my heel upwards. So he used to blame my parents that they haven't taught me a proper way to walk. So similarly with data set, you need your trained model is as good as your data set. So for instance, let's say if I am training what sort of a plant it is, I need to have good pictures. By good pictures, I'll get to it later with the dataset generation process. I need at least some good pictures of this plant to train my model. And the third one is the training algorithm and over GPUs and CPUs. Thanks to Darshan, he gave a really nice detailed introduction to what these algorithms are behind neural networks. I won't be going over the algorithms because it is very intensive. So I'll just keep it to minimal. So what are the models available? I just said a little earlier. There is Google's inception model. There is CafeNet fine-tuned Oxford Flowers dataset, if that's of any use to you. There is also this dataset, Places, sorry, not dataset model, Places CNN model from MIT. And also you can find the models in this Cafe model zoo. Cafe is the other framework compared to Tensorflow. What Cafe has something nice about them is they have a place where people who have trained their model, they can freely distribute that model there. So in there you can find the GoogleNet, you can find all the models that the modern papers are publishing. Also, secondly, I would want to mention what TensorFlow is doing in respect to this is there is this thing, a new thing in the repo. It's called TensorFlow Serving, and in TensorFlow Serving is an effort to do the exact same thing that Cafe Model Zoo is doing. People can upload their trained model, and in the future they can do work with it. So next. So that was the first part of the recipe, the model. The second part is the data set. So where is the data? How do I find a data set? So here's a website. You can go there. These are some publicly available data sets. For instance, the MNIST dataset is there, the Cypher10, Cypher100 dataset is there, and there are a lot of different datasets, Flickr images and stuff. You don't have to mine the whole web to create your own dataset. But here comes the next part. So for instance, I want to, today, I will give you an example. I want to differentiate between these two products. For instance, I have here Lipton Recipe Secrets Onion Mushroom, and I have Lipton Recipe Secrets Onion. So how do I go about that? So the 1,000 classes that Google's inception model have been trained on, they have trained on cars, they have trained on cats, dogs, and stuff. So they don't really have Lipton Recipe Secrets. Maybe what they have is probably a box. They might have just a box as a class. So since we don't have that sort of a data set, how do we go about creating your own data set? So I mentioned before that you can, one approach could be that you can look into Google, you can write just a script and mine the web to find good enough images. There's also the ImageNet. ImageNet has a big collection of over 80 million images and also labeled. You can use that. Or you can do what I did. I produced the dataset by myself. And how I did that, I would want to share with you. So this paper is by Benjamin Saab, Ashutosh Saxena, and Andrew Ng. And what this paper talks about is how to produce data for neural networks. And the need for producing data arose is because, for instance, when I was training the Google's network to recognize this product, there are a lot of parameters that you got to think of. Like, for instance, if my neural network doesn't know that, okay, this is from this direction the product looks like this, from the other direction the product looks like that, it won't be able to recognize it properly. Your recognition won't be that good. So one thing you could do is that you could manually take a camera and take all the pictures from all different directions and feed it to the network. You could do that, but that's a lot of manual labor. And it's probably going to take you over a year to completely do like 1,000 class if you want to. So this paper, it talks about how to fasten up that process, and I followed this paper and I did that. So here you see, what you see here is that I chose 10 different products, and I put them under a green screen, and I took pictures of the products in 24 azimuths and 5 elevations. So coming out of the jargons, 24 azimuths is, let's say if you have a camera, you just rotate this product on a circle, divide the circle by 24, and then just keep the product on the circle and take the image with the camera under 4 elevations. So on the screen you see there are like hundreds 100 images per product. There are 10 products up in the screen. And then you just do some normal OpenCV image processing stuff. What I did was I took some background images before, and I just subtracted out the green screen, and this is my synthetic image. So I just put the product in one of my background, and it looks kind of nice. Like it looks like it's kind of natural, but it is good enough for my neural network to learn that okay, this is Lipton onion or mushroom. So this resulted. So I had 15 backgrounds. I have 100 images. So 15 times 100, normal discrete math. 1500 images I have now for per product to retrain my network. And 1500 image is good enough for retraining in TensorFlow. But you could add lots of data augmentation, such as you could put a little rotation, you could put a little brightness, some filters you see in Instagram. You could do all those stuff in OpenCV and just generate millions of data if you want to. So a little visualization of how from 100 image it went to 1500 images with background subtraction and stuff. So let's dive into the code. So in TensorFlow's GitHub repo, they are working on publishing the actual training code for the whole inception model. It is right now being paused because of this issue with this thing called protobuf. I won't explain much about it, but if you look into it, you'll understand what the issue is. You have to go inside protobuf and you have to manually increase some bit allocation to it. So I'll come to it later, but I don't want to intimidate you with that. But what you do is go to GitHub's repo. You can see the retrain.py code. It's a simple Python code. And what it does is, so there are two approaches you can follow when you want to retrain. So let me take you to one of the last slides, actually. So there are two approaches you can follow when you want to retrain. One thing you can do is this thing called convolutional neural networks as feature extractor. So what you do is, previously Darshan explained to you about the layers and the fully connected layers. So one approach, one strategy you can follow is remove the last layer, and you define a new last layer, and you just train the last layer. So giving you that in layman's term is that, for instance, in Google's inception model, first I have learned how to recognize a car, right? Now I want to say, okay, this is a BMW. And so what you do is that, since my model already knows that it is a car, I define in the last layer, I just retrain a last layer, okay, the BMW car looks like this. These are the inputs. Now learn from these inputs and attach it to the previously learned knowledge that, okay, this is BMW car. So something like that. So you pull this code, and I won't go details into the code, because the next thing is they have a really nice tutorial. So if you just follow this tutorial, you will get started with how to use that code. It's very detailed, and it's also being developed by all the open source community. And once you have retrained your model, you have got a model, you have got your labels, how do you see that your model works? So today I'm going to give you a small demo in the Android app, but there are a lot of other examples in the repo. You can see there's one called label image, there's one with a Python. Label image is written in C++, and ImageNet classify is written in Python, and there's the Android demo, which I'm going to show today. So let's get to it. Give me a little second. Here's my app. And so this is the Android app that ships with the repo. And as I told you, I trained on this two product. If I point my phone into this product, it says it's with 98% accuracy, it's Lipton wine. After some time, you'll see like it will say it's Lipton onion mushroom, but right now my retrained model's accuracy is 89.2% to note that, so for some reason it's saying Lipton onion, but hey, it's saying Lipton onion. Let's look at Lipton onion, let's see what it says. But yeah, you get the idea. You get the idea. What I'm trying to say is just like, I just got to be more meticulous with the training. But that was an effort to show you how you can use these models, because we want to make use of these open source models and really put it into the developer community and advance the field. So if you're interested, this Android demo is still under development in the open source repo. It's not yet advertised that how you can use the retrained model with the Android demo, but it's been recently fixed. But these are the steps you have to follow to make the Android demo work. I won't go into detail, but if you want to know more, just come and talk to me after the talk. I went toward this, and so lastly, this is my last slide, I guess. Yeah.
Wait a minute, you talked about just retraining the last layer. Are there other options?
Sorry. Yes. Thank you so much for reminding me that. Yeah. The second one is fine tuning. So what I mean by the two strategy is, okay, the first strategy is going back to the BMW model, you already know the car, and you just want to put, okay, this is BMW car. The second one is fine tuning. So what I mean by fine tuning is that, so Darshan showed you all the layers of the neural network, right? So in the first method, I'm actually not touching all the first layers. I'm only touching the last layer. And with fine tuning, what I'm doing is I'm touching all the layers, tuning each of the hyperparameters that Darshan talked about to make my model even better. But there are some pros and cons of both. The pros, they do the same stuff, don't get me wrong. The pros of the first method is that it's very fast. You can do it as quick as 30 minutes on CPU. But the second one, it would take you a whole retraining time. It would take you more time than the first one. But the first one is not as accurate as you saw in the demo, but the second one would be more accurate to your needs. So this takes me to this slide, which would explain more onto the fine-tuning part. So when do you want to use transfer learning? So let's say you have a very small data set. Let's say this plant, I could only take 5 shots of this plant. You have a very small data set, but it is very similar to the original data set. So for instance, if you compare it to the 1,000 classes of the Google's inception model, the Google's inception model probably has a good number of plants. So when you have this situation, you train a linear classifier on the CNN codes. So this means you remove the last layer and just run that train PY code on that. The second situation, your data set is large. So for instance, you have a large number of, let's say, house labels. The thing, let's say 23 Berkeley Street, I don't know what to call that. But you have a large number of all those pictures. Or let's say you have a large number of traffic signs. So there is a database of that. You have a large number of traffic signs. When you have that large of a data set, and it's also similar to the original data set, you're probably good if you want to fine-tune through the full network, and you would want to fine-tune to the full network so that it's more accurate. But as I've told you, but the pros and cons, fine-tuning would take you more time, but it would give you better data. So whatever floats your boat. Third situation, your new data set is small, but very different from the original data set. So I guess for this product that I had done, I should have followed this. Because, as I've told you, the Google's inception model, it probably doesn't have a product like this. It probably just has a box. So, for instance, if you find that you are training on a product on a object which is not in the original original Google's, let's say, classes, you probably should, rather than not removing the last layer, you should probably go back to the initial layers. For instance, there is this layer called SVM layer, and you should probably start training from there rather than training only the last layer. And the last heuristic is that your new data set is very large, like the ImageNet data set, and also it is very different from the original data set. So in that case, you're probably better off training the whole model from the scratch. You're better off writing the whole model, probably, let's say, if you just follow Microsoft ResNet, just train the whole model from the scratch, and you should get to a good enough accuracy to recognize that product. And that concludes my talk, I guess. And I would really highly recommend the course from Stanford. It would give you a really good understanding of the theory. And yeah, if you have any questions on what I said, please. Thank you.
But why do you think that the demo did not work?
Why do I think the demo did not work?
Yeah.
So if you look into the products, you see the only difference is the color in the label. One is in the onion, it's only orange. The other one is blue.
Yeah.
So the difference is very minute. So one reason I can tell you is that I told you that I only trained on the last layer, but I probably should have trained from the SVM layer because it was trained on Google's inception model, and Google's inception model, I can't tell you off the top of my head, but if I go into the 1,000 classes, I'm pretty much sure that they don't really have a certain class which says Lipton recipe secrets. It would, I don't even know if they have a box, but like it was just like by magic I just saw like there was some recognition happening, but to make it really work, I should probably train a whole model from the scratch because there is no really good model out there which does like image recognition on these objects. But I could probably go back and do the SVM training from the SVM classification, SVM layer to see if this demo improves.
Could it be because of the light condition here? Maybe
it could be. It could be.
It might work.
It could be. So
I will try with a flashlight.
You would try with the torchlight?
With the flash and everything.
With the flashlight?
Yeah.
Yeah, I can try that. Maybe after the talk we can see if that works. But you're right that under specific conditions. So you saw in the previous slides where I showed I had different backgrounds and I stitched on them. So let's say the backgrounds were taken under a specific lighting conditions. But let's say if I had increased the backgrounds and had more images under different lighting conditions, that could have improved the demo. Okay.
Thanks.
Please. I'll come to everyone. Yes.
So you mentioned the possibility of like retraining the SVM layer. I didn't realize that the hidden layers correspond to like other traditional classifiers, or at least in this case of the SVM layer. So I guess my question is it common for deep networks to have the hidden layer, sort of internal hidden layers corresponding to like one in SVM and one doing some sort of like logistic classification, etc. Do you have to like hard code that stuff in Tensorflow, or how does it come to be that the internal layers correspond to regular machine learning classifiers?
Sure. So I probably can't give you a full-fledged good answer to that, but I'll tell you what I'm thinking right now. So the initial layers of the neural network, it's it's all very basic features. So for instance, let's go to the plant. Here, the initial layers would say that, okay, I can see this shape and this shape looks like a leaf. I can see this shape and this shape looks like a stalk. But I still haven't gone to the part where I'm saying that, okay, this is this species of a plant. So by SVM layer, what I'm saying is that it is one of those initial layers which determines, let's say, for instance, in the case of this product, it would determine, okay, this is a relatively small box. It has a bluish color to it. So all those generic features of this product are the first layers. So by saying that, okay, I want to retrain from the SVM layer, what I'm saying is that, okay, try modifying the ground truth behind what it is. So my mistake was that, okay, I retrained it on the last layer, but the ground truth behind those that last layer was that it doesn't even know that it is a product, but for some magic it stopped recognizing. Did I answer your question partially?
I think sort of, yeah. I mean, I guess, and another sort of simpler way of thinking about it is like an SVM is defined by, you could say, maybe the objective function that it seeks to minimize, right? The loss it seeks to minimize, the maximal margin between hyperplanes or whatever. So is that something that is like baked into TensorFlow specifically? Is there an
yes, there is. So this is, or you can find all these build files in the kernel. There is all. So one good thing about all these frameworks, Caffe 2, TensorFlow 2, all these layers implementation are already written. So you in the CS231 class, you will see that they will teach you how to write all these layers. But in reality, when you're trying to develop something, you don't really have to write all these layers by yourself. You just call all those functions from the library. But yeah, there is those layers already implemented. You just have to call it. Yeah. Please.
Yeah, in the Android, it was just the forward propagation that you were doing. Is that right?
I believe so.
And was that hard to do? Was it just Python code, or did you have to code up?
So yeah, I did not have to write any network. So what happened was I took the Google's inception model. The Google's inception model was already trained, and that has like the whole definition of the network. And I just took that Google's inception model, and in TensorFlow, if you go into the retraining code, you'll see that what the code does is that it just calls on the last layer, removes the last layer, and it makes a new last layer with empty weights, not even empty weights, like very randomized weights.
So that was for training. I was just curious about your Android demo.
Oh, for the Android demo, you just load, after you have retrained the Google's inception model, you get a .pb file, and you have a label. So you just load those two files as assets into the Android demo, and you just make some modification in the Android demo's classes. You put some, so these have input size, image input size. They have image mean, and they also have the standard deviation. So this is what I had to do to make it work with the Android demo. I had to modify the TensorFlow gni.cc, which is the method that Android talks to the TensorFlow stuff. I just had to make the input tensor name as small. I had to make the end tensor name as final result. This is just how the architecture of the Google's inception model is. That's it.
So is Android talking to a backend, or is the inception model provided also to run on Android?
So the inception model is is in the phone right now as asset, and this TensorFlow.gni.cc, it is able to read the inception model and do stuff with it and talk to the classes in the Android.
And about how long per run is it taking?
So it is nearly 01 time. It's a constant time, because that's the best thing about neural nets is that once you have done training, your lookup time is always constant, nearly constant. So this camera runs like 30 frames per second. So every frame it is doing its image recognition.
Thank you.
Please, Abby.
So what was the hardest thing that you've done so far in developing your modified model?
So the hardest thing was getting this Android demo to work. That wasn't because of me, but that was because so there is this thing called protobuf. Protobuf is the format of how the models are supplied. It's a Google's format of how to ship these models as universal as possible so that it works in different devices. So that protobuf model, there is a problem still now. There is a problem. It hasn't been solved yet. You have to increase this bit allocation to it. I had to increase. I didn't know that I had to increase, but I had to increase it from 64 bits to 256 bits. That was one problem. And the second problem was this Android demo. It still hasn't been updated in the repo yet, but this Android demo actually uses an old inception model where the names of the first and the last layer are different. So one challenge was just to figure that out, that it was different. Once I figured it out,
So basically just little technical
just little technical problem with the hardest part.
So I have another question, which
yeah,
is,
sure.
you keep talking about the Google Inception model. There's a few of these models that people have really run through all the way. If you had a much wider variety, would you shop around? I mean, is there a need for these sort of starter models?
So are you asking that you want to, let's say you want to use different models to accomplish a specific task?
For learning, you start with a particular model.
Yes.
It doesn't sound like there's very many of these models. There's lots of magic numbers and training that go into them. Is there a need for a lot more of them, or are they just need?
Lot more of models.
Yeah.
It is very good in practice because when you are training a model from the scratch, you start with a very high, very arbitrary weights for all your parameters. So it saves you time, and who doesn't want to save time? So retraining on even let's say the last case in the even with the last case in here where I'm saying that your new dataset is large and very different from the original dataset, even though you could train from the scratch, in practice it is really better that you take one of the already built models, like the Inception model, which trains on very large dataset, and train on top of that, do fine-tuning and train on top of that. It's good in practice because you would save yourself some time, and because right now one of the limitations of deep learning is the hardware itself. GPUs are costly. Yeah, that's still an area of research. Please.
Have you come across any extremely successful application of transfer learning where the new data set is small as well as the data is extremely different from the normal ImageNet or the trained model or the model where it is previously trained on? So I have come across some of the research articles where models trained on ImageNet has been applied to medical images. So, have you come across any other successful applications where suppose models trained on ImageNet is applied to satellite images or some other hyperspectral images?
So I haven't I haven't seen any of those applications. Maybe in the future I'll read about it, but yeah, I haven't. Yeah.
Thanks. There are some cool ways to do data augmentation.
Yes.
For example, Alec Bradford was able to do really well on the MNIST classification by using a generative adversarial network to make more digits, and then retrain on the generative images that we make. We make like millions, billions, and then retrain and score even better. That was really cool.
Yep.
Do you know of any other really cool techniques for augmentation?
So I shared with you about the green screen. Other data augmentation techniques. Yeah, like I told you about, you could use different sorts of filters, you could use different rotations and stuff. Those are like the standard techniques that I've told about. Yeah, I don't know, like right off the top of my head, I think it needs more, like I would have to research, find out like a cool way to do this, generate this synthetic image. Like,
Well, I mean,
yeah.
just in the adversarial treatment, would it be considered transfer learning if you were only training on things that got wrong? You know, you started with everything got right. Would that be a form of transfer learning?
Once again, what did you said that you're training on something that is wrong?
Well, you just if you're always looking for things that it got wrong, right, instead of just running it through the whole training set.
So I think you're referring to training set and a test set. Is that what you're referring to? Let's say once I have
No, I'm
training.
just referring to how you would normally train something, which is once it was getting most things right, you would only train on the stuff that got wrong, which actually fits your model of transfer learning. You're
Okay,
starting with
okay.
a model that got a bunch of stuff right.
Okay. I'm sorry, I really didn't get the question. That's fine. Yeah. Please.
I just, this is not a question at all. I just, please re-emphasize what you said, that training is expensive, and go ahead and use what's already been trained. And what he was trying to say is like a sort of recursive training on whatever failed sort of thing.
Oh, okay. Now.
Repeat what you said and say like training is very expensive, and that's not a question, but
Yes.
just I really think you should repeat that 50 times over, so don't go and retrain everything.
Yes, training is expensive. Sorry, sir. I got your question now. Yes, you could do that. If you could do, let's say, if your retrained model, let's say, for instance, mine is not correctly recognizing as of now, I could go back again and I could supply it more of the data of, let's say, this little onion mushroom, and it would become better. But one thing we should be cautious about is not to overtrain, overfit. That's what Darshan talked about. That is, like, if you provide all the different conditions, in the training phase, it might not be able to correctly put like, okay, this is true and this is false. So that's one thing about cautions. And yes, training is expensive in GPUs, but there has been active research going on in the hardware side. There has been Altera produced a white paper on how to train in FPGAs. FPGAs are very inexpensive compared to GPUs. Also, there has been good research on, right now, somebody got a $12 million fund. It's on recurrent neural networks, and apparently they don't require as many data sets as possible. So that's another thing to be kept in mind. It might be just in 6 months you would see no point of producing all these millions of synthetic data. TensorFlow, does it work with? I haven't worked with it, but it should. It does. Yeah. Yeah. Any other questions? Please.
This model we started with, how many images was used for training, and how many object classes they recognize?
So
It's an inception model. But obviously, like billions of images were used, right? And how many classes for objects that you can have?
So the Google Inception model was trained on 1,000 classes. Total image was 1.2 million images.
Okay, so 1,000 classes. So what are those classes?
So cats, dogs, train, car.
Okay, and it has a few layers, right? Like 5 or 6 layers, right?
The Inception model?
Yeah.
The Inception model is actually about over 26 layers.
Okay, so let's say if I just remove the last layer, what does it recognize? It still is a model, right?
Yep, that's a very good question. If you remove the last layer, so for instance, I have fed it an image of this plant, asking, okay, this is, I don't know what sort of plant this is. Let's just give this an imaginary name of this plant. It's called Tom. I have given the picture of this Tom plant into that, removing the last layer and given that image, like what this plant is, it would probably say that, okay, it is kind of looking like Tom, but I'm not sure. It is Tom, but it has like 5 leaves with like green and white.
But is it possible in general to say, okay, that this model without the last layer recognizes 3 something, or let's say 3 million of different things? Can you name them? Or is it possible at all to understand, let's say, what's going on inside?
So I understand your question. So if you remove the last layer and then
let's say you remove the last layer, right?
Okay.
And then you show let's say the set that was trained on. How many different answers will be there in the last layer?
Okay, so let's come up with an example.
And what are those answers? Okay, so you'll put there like all your training set, and maybe you will come with 3 answers.
Okay.
Who knows?
So yeah, so let me give you an example. The example is of a car, and so you have removed the last layer, and now what would my model say on the car? It won't say that it is a car. It would say that, okay, I can see a tire, I can see a shape which looks like it's the mirror of a car. I can see that there is probably a windshield, but it can't deduce, we're using all those different things that it has found, that it is a car.
Let's say I'm an layer. Okay, so I take original data set, I remove the layer, cut it off, and I feed it, okay, and I came up with, let's say, 3 million of distinct answers. And only 3 million, right? So I cannot say what these 3 million things are, right?
Okay.
I mean, I show you the car, and it comes with the answer 3045. I show you, let's say, a human being, and it also comes with 3045. Is it possible? I cannot classify. I cannot understand what it does, right?
So yeah, you as a human, you cannot, like as a computer, you cannot understand, okay, how to make sense of that data. But yeah, like probably the numbers are a little overestimated. But
so what I'm leading to is that
yes.
I mean the whole approach, right? They train you, okay, let's say with your boxes, right? I mean, how do you know, let's say, that removing layer, okay, let's say, is conducive, I mean, would work at all. It's just like a philosophical, okay, it's not good at all, okay? I mean, it's jiggle. So you remove something from the black box,
yeah.
You remove like a slice of black box, now you remove the stuff I want, now you're hoping that it will work.
So it's not hoping, it's mathematics.
You just practice, I don't see mathematics there.
You don't?
So I think what might help here is your last layer is what's responsible for giving you a number that means which class it is.
Yes.
When you say remove the last layer, what you really mean is reset the weights and have a new output vector
Yep.
that may have a different number of classes.
Yep.
But you're still taking a very large vector and then coming down to a smaller one.
Yep.
So
Yeah.
that, I think, so his question is, that what makes it confusing is,
Yeah.
the second to last layer's output is a ridiculously large vector that we don't make sense of.
Yeah.
It's only the last layer that gets us to a smaller vector. Right? So when you say remove the last layer, what you really mean is, and then add a new one that you train on.
Yep. Yep.
How useful is the last one layer? I mean, it produces, let's say, some huge number of numbers, okay, which you know nothing about.
Sure. So what you have to remember is that the entire network internally, it's all numbers. It's all numbers. We apply our semantic meaning to those numbers. So at the last layer,
Only the last layer.
So at the last layer, what the actual output is isn't cat, dogs, whatever. It's a very long vector that's mostly zeros, and then there's a 1 at the cat slot. And then there's another 1 maybe, or a 0.5 or something at the dog slot. Say it's a picture that's hard to distinguish between a cat and a dog. But what you get is a very long list of numbers, most of which are very low, and a few of them are high. And the softmax that we talked about is where we say, okay, which one's the actual highest? That's what we're going to call it. We're going to call it a cat. But we apply that semantic meaning to a very long list of numbers at the very last step. So when he says remove the last layer, what he's saying is take out the weights, the little multiplications that happen to produce that last layer, and now we're going to have a new one that's randomized.
Right, but you remove the meaning, right?
We're removing the meaning.
And so what's exposed, okay? Some things without meaning. Okay, the last, let's say, all these 25, right? So now, let's say, I mean, what gives you, theoretically, philosophically, okay, hope, okay? That in this network, okay,
What makes your
which was
question,
totally meaningless, okay?
Well-
you just retrain the last layer and you will get results.
what makes your question difficult to answer is, you're asking the same thing of like, what happens when a neuron fires in the brain? What does that mean?
Yeah.
Right? What does that semantically mean? Like, this neuron fired, how can we make any sense of that? Well, of course we can't, because we speak in language that's higher level. And so when you try to ask the question, like, when we just slice off the layer and look at what's inside, it doesn't have semantic meaning. And so
That's
we
not
use-
entirely true. What
I mean,
he's-
you make a black box
No,
commitment.
no, no, it's not entirely
You
true.
just base it on performance.
Maybe we should take this offline.
Yeah, okay.
Thank you.